Cool. So let's talk about measurement and visualization. We're doing part 2 today. So we're going to do more talking about particularly survey design and how we do measurement in the social sciences. But we're also going to do a little bit more with data visualization and graphing. So that's kind of the general theme for today. So we're going to cover survey methods with randomization. We're going to cover administrative data and agency surveys, which are something that we use a ton in the criminal justice field, but also in any field that interacts with government agencies, you're going to use administrative data very frequently. We're going to talk about unit and item non-response within surveys and how to think about different kinds of non-response and missing data. We're going to think about desirability bias. We're going to think about latent variables and latent groupings, latent meaning unobserved or underneath the surface. And we're going to do some more work with data visuals. Oh, my apologies. I haven't pushed them up. Let me do that. Thank you. Thank you for the reminder. Okay, now you give it 30 seconds, they should be up along with the homework. Okay, yeah. And we'll kind of, yeah, I just remembered I want to talk over a couple things on homework 4, which everyone did well on, and I was pretty happy with the quality of the work. I noticed a lot of folks were using the base R code as it was demonstrated in the textbook, which is totally fine. I just want to make sure that I'm showing you how you could translate that base R code into tidyverse code too, because I'm showing you one way of doing things in class. The book is showing you effectively the way that it will work just fine. It's called base, and it's the sort of standard R way to do things. But tidyverse, I think, really expands on and makes those kinds of operations easier. So I want to make sure I can show you how to translate that as well. Okay, so surveys and censuses. We distinguish between a survey and a census in that a census records information about a full population, right? So we typically think about the US Census is kind of our canonical example of this, right? Records every 10 years information about the entire population of the United States, right? Every single resident of the country, every single household of the country, rather, is surveyed, right? And so in an ideal world, right, assuming the census is a perfect measurement, we get information about every single individual in the United States who has a residence in a household, right? So in theory, we cover the entire population of people in households in the United States, right? Now, there are people who live in the United States who are not in households, right? So people who have housing insecurity, who are homeless are not necessarily included in that population. And so that's one thing to consider. But in theory, it's measuring the full population. Another kind of census we can think about is the National Prisoner Statistics. Captures data on every person who is detained in a state or federal prison annually, right? So that's another census. We get information on every single individual who's housed within a facility annually, right? It's not a subset, it's everybody. So a census is any data set that contains, at least theoretically, complete information about a population with measurement for each individual or unit in the population. It is comprehensive. A survey, on the other hand, samples from a population. A survey is a subset, right? Where if we can think about this in terms of like our Venn diagrams or set theory, a population would include all members, right? This would be the census. A survey might capture information about a subset. Right? It's capturing a subset of that larger population. And our goal with the survey is to use information that we collect from this subset to make inferences about the larger population. An inference is using data from a smaller group to make a judgment about what a quantity of interest may be for a larger group, right? So we're going to use information from our subset of the data to make inferences about the population. That's usually what we're after when we're collecting a survey, when we're collecting a sample from a population. And so in order to have valid inferences, we need to be careful about who we include in that sample, right? Because we could imagine that, like, let's say this is age over here, right? And let's say that on the right-hand side, we are kind of sorting people by age. And if we grab this sample over here, we're missing out on all the younger folks over here. We're only grabbing people from this group. So if we use only this sample to draw an inference about this larger population, our estimate for the age of the population will be too high, right? So we have to be really careful about which samples we collect if we're hoping to learn something valuable about the larger population, to have a valid inference. So here's the basic motivation for survey sampling. What I'm doing here, you'll see this notation. Does anyone know what this is? 1e6? So that's 1 times 10 to the power of 6, right? That's just scientific notation. And it's an easier way than writing a million, right? Writing 6 zeros out there. So I'm going to just effectively, this is 1 with 6 zeros. I can use this notation to make large numbers a little more compact. So I'm going to say make n equal to 1,000,000. And then I'm going to create a data frame called marbles, where I'm going to have blue, green, and red marbles. Each will have 1,000,000, right? So I'm going to have a color vector that will have 1,000,000 blue marbles, 1,000,000 green marbles, 1,000,000 red marbles. So my data frame has a single column called color, but we can think of each row as being a marble. So I've just created a bag with 3,000,000 marbles in it, right? 1,000,000 of them are red, 1,000,000 of them are blue, 1,000,000 of them are green. Now, this is obviously an absurd thing to do in practice, but this is kind of why simulation is fun, right? Okay. So everyone kind of follow that. You don't need to be able to replicate this code. This is when you see things like this is me just demonstrating how I did it. But effectively, we're kind of setting up this experiment where we have 3,000,000 marbles evenly divided across colors. Now, let's say that like the blue marbles are a little heavier than the other marbles. We don't know that, right? But let's say there's an unobserved trait where the blue marbles are a little heavier. So if we just like take from the top of the bag, we're going to systematically miss those blue marbles because they're going to sink to the bottom, right? So we have to be cautious with how we draw our samples. The method we use can impact what inferences we make about what's in the bag, right? If we only draw from the top, we'll say, oh, okay, this bag is full of green and red marbles, and we will never know that there are any blue marbles in there at all, right? Because they're all at the bottom. So we need to think about another method that will help us ensure that we actually capture what's in the population accurately. So how could we know how many of each color are in this enormous bag of marbles? First thing we could do is we could conduct a census where we dump the bag out and we count every single marble. But that's quite tedious, right? And in real world kind of terminology, right? That's cost prohibitive, right? It's incredibly expensive to conduct censuses in terms of time, right? In terms of sort of human hours of work that it takes to do a thing. right? That's quite laborious, quite tedious. Or we could sample. We could say, let's select some of the marbles from the bag and use that sample to make a guess about what the composition of all marbles in the bag is. We may not know exactly how many there are, but we can figure out what the proportion is, right, across groups. Now, the key to this, here's a plot, right, with just all of the data. So I'm going to do a ggplot of marbles where X is going to be equal to color, and I'm going to do a bar plot, right? A bar plot gives us a visual where the bar is equal in height to the count of the values in each of the cells, right? So our three values here are blue, green, and red. Sometimes when I have a discrete or categorical variable, I'll say cells for the number. I'm thinking of it as a table, right? So we can think about how many counts are in each of the cells of the table. So we have 1,000,000 blue, 1,000,000 green, 1,000,000 red, right? The height of the bar is equal to the number in each color. But how many random draws would be enough for us to accurately measure the distribution of the 3,000,000 marbles? How many draws, how many random samples? So let's assume that the weight is identical across them all. We shake the bag up really good and we draw out marbles. So let's say I draw 5, right? Now, these plots will look different every time I run it because it's a random process, right? But in this case, I drew 5 marbles and I got 20% of the marbles were blue, 20% were green, and 60% were red. In other words, I got 3 red, 1 green, 1 blue, right? So that does not accurately reflect the true distribution of the marbles in the bag, right? We know that because this is a simulation and we're effectively, pretending we're a god and created this bag of marbles and we know the truth. But usually in practice, we do not know the truth, right? We have no idea what the true population levels are. And so we're using our samples to make best guesses, but we can use the properties of random numbers to understand what an adequate size of a random sample needs to be to get good inferences. So what do we notice? Okay, now let's go to 10. So before I do that, what are we looking for this bar? What are we looking for the height of the bars to do in order to tell us that our method is generating an accurate inference? We're looking for them to be equal, and where should they level? Where should they be? What level should they be equal at? 0.33, right? 1/3, right? This is proportion. So we expect the height of each of these bars to be 0.33, right? That's the truth, and we know that. So we can use our simulation method here to think about when is it that we see those bars start to kind of come together and stop moving around a lot. So obviously at 5, we're at 0.6 and 0.2. That's really far from the truth. At 10, we're at 0.4 and 0.3, right? So this tells us on this sample of 10, I drew 4 red, 4 green, and 4 blue. Or 4 red, 3 green, and 3 blue. If I run another sample of 10, I could get very different results, right? But that's what I got this time. This sample of 50, I see that I've got like 0.42, like 0.32, and maybe, I don't know, 0.28, 0.26, something like that, right? So we're getting closer. We're kind of coming closer. We're kind of waiting until they all converge. All 3 of those bars come together at that 0.33 line. When we're at 100, right, we can see that we've kind of shrunk a little bit. 300, we're kind of all are below 0.4, all are above or at 0.3, right? At 500, we're looking pretty similar to 300. By 1,000, we're very close. All of these are very close to 0.3, right, or 0.33. We call this sampling error, right? So we're always going to have a little bit of wiggle around the truth. The truth here is 0.33. We know that, right? We don't know that in practice, but here, because it's a simulation, we know it. And so we have a little bit of deviation from the truth, right? Every time we randomly sample something, we are very, very rarely going to land on the exact truth. And when we do, we won't know it, right? Because we usually don't know the truth. Otherwise, why would we be doing a study? What we're going to end up with is a bit of noise that we have our kind of result from the survey, or what we could call our sample mean, that differs randomly from the true population mean, right? So in stats language, we would have our sample mean, X bar, and our population mean, mu. We're using X bar to make an inference about mu. We don't know mu in practice. We want to learn mu. Because this is a simulation, we know that mu is 0.33. What we observe for X bar, for blue, we observe that in our sample, the average ball had a probability of about 0.2 of being blue, had a probability of 0.6 of being red. We can describe sampling error as mu minus X bar. Actually, reverse that, X bar minus 1. Usually we're going to square it and take the square root of it to ensure it's positive, so the direction doesn't matter too much, because we want absolute error rather than directional error. But sometimes we want directional error. So let's do X bar minus mu here. For red, when our, let's say, what do we observe when n equals 5? Let's say X bar red, we'll plot X bar for red is equal to what? What do we observe when n is equal to 5 for X bar red? That is, what is the average probability of having one ball be red when n is 5? 0.6, right? We observe that 0.6, 60% of the data was red. So our estimate, our statistic for X bar for red is 0.6, right? Now we know the truth here. What is the truth? Mu red equals 0.33. Yeah, we'll just round. 0.33. So our sampling error, call it error, equals X bar red minus mu red, or 0.6 minus 0.33. Right? So in that case, we have an error of like 0.27. Our guess for how many reds there are will be too high by about 0.27, but that's random, right? If I drew that sample again, and let's just see what happens when we do it. There's our marbles. And then let's do a sample of marbles color. We're going to do 5, replace equals false. We can sample with replacement and without replacement. We'll talk about that later. Basically, replace tells R, when I draw the marble out and I count it, do I throw it back in the bag or do I not throw it back in the bag? In this case, I do not want to throw it back in the bag. Sometimes we do. Okay, so this time I got green, red, red, blue, green. So what is X bar red for this sample? How many reds did I get? Out of how many total? 5. So 2 over 5, 0.4. Right? So my X bar red now is 0.4. So now I can compute it again as 0.6 minus 0.4. I'm sorry, 0.4 minus 0.33 to get a sampling error of 0.07. So the sampling error is much smaller this time around, but that's pure chance, right? We have effectively a range of possible errors that we could observe for this statistic. We're going to talk more about this toward the end of the semester, but this is called a sampling distribution of the sampling error, right? Which is weird, but effectively, because of the laws of probability, as our sample size increases, the possible range of this error decreases. For small samples, the range of this error is high. For large samples, the range of this error becomes lower. Our guesses become more accurate as we draw a larger sample. Our estimates of X bar become closer to mu as the sample size increases, such that if we have a sample size where n is equal to the population, X bar is equal to mu, right? But we don't necessarily need to be exactly equal. Once we get to 1,000, let's actually just compute this real quick. So let's draw 1,000. I'm going to call it sample. Replace equals false. I'm using the sample function to give it a vector, Marble's color. Sorry, let me move this. Yeah, it's still in the same location. It's still at the bottom of the screen. That's fine. Okay, so we can see that I'm going to create a vector called T. That is a sample of the vector color. I'm going to draw 1,000 random items from it without replacement. So I'm sampling 1,000 without replacement from the vector color, putting that in an object called T. Okay, now T is just going to be 1,000 marbles, randomly drawn from color. So let's look at a table of that. What do we have, right? We have 350 blues, 306 greens, 344 reds. So what if we did T counts color? So let's do a summarize. And we'll group by color, summarize n equals n, and the n function will just count elements within each group by category, and then we'll do proportion equals n over n row t. I need to load tidyverse first. So this is going to, in your homeworks, a lot of you did the prop table function, which is what was demonstrated in the book. This is a similar way to do the same thing in tidyverse. We can count each group, and then oh, it's a character, isn't it? Okay, sorry, this is not working as well as I would like. Okay, so T as data frame T. I got to convert it to a data frame for this to work. Okay, sorry, this is a little more tedious than it should be. Okay, forget it. Let's just do this by hand. Okay, 350. We know there's 1,000, right? So let's compute our errors here. Sometimes it's easier to do it by hand. X bar blue is equal to, what's our count for blue? 350. And what's our N? 1,000. X bar green. 6. X bar red. What's that? 344. Okay. So we end up with 0.35, 0.30, 0.344. Now to compute error, right, we can difference those off of the truth. Now in this case, those errors are really small, right? The error here is 0.02. The error here is like negative 0.02. And the error here is also about 0.02, right? Now relative to the estimate, 0.33, 0.02 is pretty small. So in this case, we could say, now we'd want to actually do the math to ensure it, but we have about a 0.02 deviation across all of our categories from the truth with a sample size of 1,000. Now for our question, we can ask, is that an acceptable margin of error? Do I need to be more precise than 0.02? Sometimes I do, sometimes I don't. If 0.02 is an acceptable margin of error, cool, 1,000 is all I need. I do not need 3 million, right? Now we'll tell you exactly how to compute those margins of error when we talk about standard errors later in the semester. And we'll talk about that in terms of power analysis, which is a method we can do to figure out how certain do I need to be about my quantities of interest? How certain do I need to be about mu? And then if I know how certain I want to be, and I have a guess about where mu is going to land, then I can do what's called a power analysis to see how large of a sample size do I need to obtain a particular margin of error or confidence interval, right? Those terms are describing the same thing. Okay, questions so far? Yeah.
We're going to talk about like how to do power analysis at all.
Later in the semester, yeah. I mean, in a really shallow way, right? Power analysis is obviously something that can be very complex depending on your study design, but we'll talk about it. Effectively, once you know how to compute a standard error, you know how to do a power analysis. You're just solving for n instead of solving for, usually we're going to solve for mu, but in a power analysis, you assume mu and solve for n. So it's a really simple process once we understand the equations.
Okay.
Yeah. Power analysis can be useful, particularly when you're designing experiments and you're thinking about how large of a study do I need to design to detect an effect if the effect is of a magnitude that I theoretically suspect. Right? Okay, so what do we see here? First, we'll talk about why this is later, but we can see that once we get to a sufficiently large sample, honestly, usually around 100, right? And we could replicate, let's just like, so we can see it bounce around. I kind of like visualizing randomness a little more than I should maybe, but let's look at it. So that's one run of it, right? Let's run it again. That's another run of it. That's another run of it. And we can kind of work through these. So let's kind of flash back. Okay, so 5 is all over the place, right? The sample size of 5, we really don't know where mu is for any of these color categories, right? Our highest is 0.6 that we observe. There, did we observe higher than that? No, the most we ever got was 3 out of 5, but we did get a lot of 3 out of 5. 10 is also jumping around a fair amount, right? And this is just 5 samples, but or four plots, right? So it's 4 examples of the errors we could observe, right? We're kind of, what we're doing is we're actually constructing a sort of set of sampling errors here. It's just weird, but that's the kind of stuff, that's actually the foundation of statistical inference, is thinking about distributions of errors, right? That's where our inference is going to come from, is when you think about a problem, imagine in your head the repeating the experiment many times. When we simulate, we can just do it, right? And so we can see where could the errors have landed? Where could they have gone? So here we can see 10 jumping around a little bit, right? Let's think about at 50, it's still moving a lot, right? Let's look at 100. Oops, yeah, I know. Stop. Okay. 100's moving less. 300 is moving hardly at all. 500 and 1,000 and up are also not moving much at all. So once we get to 300, we see about as much movement as 300 as we do in 500. And not much more movement in 1,000, right? So we could use just this simple plot to say, you know what? 300 is probably enough to get close. Now, if we want to be super precise, maybe going up to 5,000. If we want to have a really, really, really precise guess, let's look at whether 5,000 moves at all. It does in that first one. That's actually just the scale of the plot changing. Yeah, that's the scale of the plot. Sorry, I should have constrained that. So let's look at this box right here and see if it moves. Really doesn't, right? And if we compare 5,000 to 100,000, we're not really gaining much by drawing 100,000 rather than drawing 1,000 in terms of precision, right? We're guessing, we can think of what this level is as our guess based on the sample, X bar. We're going to guess basically the same thing with a sample of 5,000 and a sample of 100,000. That means those 95,000 extra samples you drew are not actually providing you with more information, right? Relative to the quantity of interest. If your quantity of interest is mu, the difference between a sample of 5,000 and a sample of 100,000 in terms of how much you've reduced your sampling error is small. There's an inverse quadratic relationship here, which we'll talk about more, but the square root of n is in the denominator for your standard error, right? That is the standard error it shrinks as a function of the square root of n as sample size increases, right? And we'll see how that plays out in practice when we get to the end of the semester and talking about the actual computation, but it's not linear, right? That is, as we increase our n, the standard error shrinks pretty dramatically, pretty quickly. So we don't actually typically need very large samples to get accurate inferences, assuming we have good samples. Our samples can be biased, and then our inferences are going to be garbage, right? But if we have an unbiased random sample, we can take a pretty small number and get pretty accurate inferences. For a data set with 3 categories, once we're at about 300 to 500, we can get within a point or two of the truth reliably, right? So that's great. That's the entire logic of survey sampling in a nutshell right there. We sample from a population because the gains in information we make by increasing our sample size over particular amounts, if we have a good sample, are negligible, right? The gain of increasing, the gain in error reduction of increasing, in this case, your sample from 5,000 to 100,000 is incredibly small. We gain very little in terms of new information. But that would take a lot of time to count 95,000 more marbles, right? In this case, I would look at this and say, I think I'm going to stop at 300 and be okay with that. Kind of clear on, as our n goes up, our precision increases. And this is the logic of the survey sample. A simple random sample, meaning when we say a simple random sample, we mean that each marble has an equal probability of being drawn from the bag. And what's the probability of drawing a marble, one marble from the bag in this case? How many total marbles do we have? 3 million. So the probability of one marble getting drawn is 1 over 3 million. Every single marble in that bag has a 1 over 3 million chance of getting drawn. And they all have the exact same probability of getting drawn. That's what we mean by a simple random sample. Every single element in the vector has an equal probability of being selected. It's not affected by anything. It's a uniform distribution. Everything has the same probability. Yeah.
So is this what's meant by the law of large numbers?
This is the law of large numbers.
Okay.
The law of large numbers in statistics is that as our sample size increases, our statistic converges to the truth. our sample statistic converges to the population statistic. Or so rather, our sample parameter converges to the population statistic. I had that backwards. Our sample statistic converges to the population parameter. A parameter is an unknown. A statistic is what we observe and compute. Okay. So mu, in this case, is our parameter of interest. X bar is the statistic we're using to make a guess about where mu is. Okay. So with a sufficiently large sample and an equal probability of sampling for all units in the population, a simple random sample allows for unbiased measurement of population characteristics. Unbiased means that on average, the sampling error is 0. It doesn't mean it will actually be 0 for any single sample, but it means that we have as much of a chance of observing a 0.35 as we do a 0.30. It's not systematically higher or lower than the truth. It's centered exactly on the truth. And we have an equal probability of being a little too high or a little too low. When we say something is unbiased, we mean that the errors will average to 0 when we sum them all from the sampling distribution. If we were to look at all possible samples from a population, right, all possible samples that we could get under some method, and then we were to compute up all of the errors that we could get from all of the possible samples, an unbiased process will result in the average of those errors being equal to 0, meaning they'll all cancel each other out. There's going to be as many above mu as there will be below mu. We have as much probability of guessing too low as we do of guessing too high. If we systematically guess too high, we would describe that as a positive bias. If we systematically guess too low, we would describe that as a negative bias. And you'll see those terms used in statistics pretty often. This estimator is positively biased relative to the quantity of interest, right? Meaning this process is going to generate estimates that are usually too high, right? Or it's negatively biased. It's going to generate estimates that are too low. A lot of times in practice, we have to tolerate bias, right? Because we can't often generate simple random samples. It's kind of tricky to do. And then your question will kind of determine, am I willing to tolerate positive or negative bias more readily? What magnitude of bias am I willing to tolerate? And you're going to have to think carefully about your question and where the data comes from to make those judgment calls. But that's kind of the core idea of bias. Is it away from the mean? And in which direction is it away from the mean? Too high or too low? And that is, does our sampling procedure systematically result in estimates that are different from the mean? If we have a simple random sample, on average, the error will be 0 with a sufficiently large number of samples. Yeah? That's the law of large numbers. It'll converge to 0 when n is large. Yeah? Okay. So we have an identical motivation for randomization in experiments, right? With a simple random sample and a sufficiently large n, our estimate of the sample average treatment effect will be unbiased relative to the truth, which we can't observe, right? But we could make our guess about the counterfactual, right? And then average over our treatment and control groups to get our sample average treatment effect, difference those. If we've randomized exposure to treatment, we will have an unbiased estimate of the sample average treatment effect, right? Same logic. So randomization is kind of a silver bullet that can solve a ton of statistical problems. Such a sample, if it's random, is representative of the population across both measured and unmeasured characteristics, right? These will be mathematically identical, right? In theory, with a large enough n and with theoretical replications. That is, if we were to run the study many, many, many times, usually in practice, we only run it once, but if we were to run our sample many, many times, as we did here in our simulation, right? In theory, each of the samples that we get will have the same characteristics as the population. And they won't systematically differ from the population in any consistent direction. However they differ from the sample will just be random, right? and it'll be random within a window that we can understand. Okay. So where are we at time, guys? Are y'all okay if we keep going for a sec, or do we need a break? I'll keep going. Okay. We'll take a break in just a little bit. So stratified random sampling is an extension of the logic of random sampling. But sometimes we want to learn about particular subpopulations. Like, for example, maybe we want to learn about counties in New Jersey, right? And in order to learn, maybe we don't want to have a simple random sample of the state, but we think the counties, or maybe even cities, are sufficiently different that we want to learn about each of these units as elements within a population. So the population will be New Jersey, but then we think that populations are kind of clustered within cities, right? And so maybe we want to sample from Newark, and then maybe we want to sample from Trenton, and then maybe we want to sample from Patterson, right? And then maybe we want to sample from Princeton, whatever, right? We want to draw all these different cities into distinct subgroups, right? And we can stratify our sampling process according to that data structure, right? According to those subpopulations of interest. So if we have a grouping in our data that we're interested in understanding, for example, perhaps it's cities, maybe we're studying an elementary school and we want to stratify by class, right? So we want kindergarten, first grade, second grade, third grade, rather than just drawing a random list of students, maybe we want to learn something distinct about each of those classes. So maybe we'll sample within each of those units. This is called a stratified sample. Okay, so we're going to subset our larger population into distinct groups and then sample among those groups. It's called a multi-stage or a stratified sample. So we can randomly sample. If we want to make accurate inferences about the larger population, we can randomly sample the larger units. In this case, let's say instead of just New Jersey, we're interested in learning about the population of the United States, right? We can randomly sample municipalities within the United States. Then we could randomly sample individuals within those units. So we could have a two-stage design where we randomly select which parts of the country we're going to draw people from, and then we randomly select people from those places. This is what the American Community Survey does, which is our tool that we use to make judgments about the US population between the 10-year census periods. So the American Community Survey every year does a sample of 1% of US households. And it uses a stratified design to do that. Or what it does is it takes census tracts and gives them equal probability of being sampled. And then within those tracts, they subset to households and give those households equal probability of being sampled. Over time, every tract gets data points. So like if a census tract might be in Newark, it might be a block or two, right? And then within that block or two, we could have 200 to 300 residents. Usually a tract has 200 to 300 residents, right? So every year, each tract has a probability of being sampled in the country, and the entire United States is divided into tracts, right? And that includes rural and urban places. And then each household within that tract has equal probability of being sampled once we select those tracts, right? If we do this correctly, we can still obtain an unbiased estimate of population characteristics if we randomly sample the larger unit and then randomly sample the subunits within it. Maybe we're interested in learning something about a particular place, though, right? That's not, we could do a purposive sample. It's a weird word. We could intentionally select, they call it a purposive sample, but it's basically just like, I'm choosing this deliberately. I hate that word. So you could deliberately choose a unit, like I want to know about Newark. I could just choose Newark. Now I'm not going to necessarily be able to use what I know about Newark then to make judgments about the entire US population, but I could randomly sample Newark and learn about its population. And sometimes that's something we want to do, right? So the stratified sample is a really flexible tool that allows us to ask different kinds of questions. And in practice, just about every survey you're going to see is going to be a stratified random sample. Sometimes it's because it's costly to obtain a list that you can draw a random sample from, right? So if we want to do a random sample of the US population, First, we would need a list of everyone in the United States, then assign them equal probability of being drawn into a sample. But if we wanted to do a stratified sample, we could first select, say, 500 census tracts, and then from only those 500 we selected, get a list of every resident or every household within that, right? And then randomly sample from there. And that's obviously a lot less work to construct what we call the sampling frame, right? When we stratify. The sampling frame is the list that we sample from, right? It's the list of things we sample from. We know it's very easy to have a list of all tracts in the United States. We just look at a map to do that. But to have a list of every single household in the United States is quite difficult, right? So sometimes this makes the process a lot easier. So the ACS method is effectively take a list of all US Census tracts, randomly sample households within tract based on a complete list of addresses. That's the sampling frame, right? We have every residential address in the country that the US Postal Service delivers to, right? And then we randomly sample those. And then we randomly sample adults within the household. So we actually have a three-stage sampling procedure here. First, we sample tracts within the country. Then we sample households within the tract. Then we sample adults within the household. Yeah? And if this randomization is done well, then we can make a guess about the larger population with a sufficiently large sample size and assuming that the randomization is valid. Which means that like our list of addresses is accurate, our list of tracts is accurate, and people don't lie about who's in the household. Right? That's when I say the data is valid, it means it reflects the underlying truth, right? Okay, so that's stratification, right? Data that we work with will often be stratified. Stratified surveys can get tricky to work with because they often have weights and other kind of complex things that you have to adjust for, but it's totally doable. And I believe we do offer an advanced survey. I believe there's an advanced stats class on survey analysis, is there? I could be wrong, but there's a whole discipline of statistics. There's a whole subdiscipline of statistics dedicated to survey design and survey analysis. There's a really well-established field for how to do this. It's complicated, but assuming this is the kind of work you're doing, you wouldn't be alone. Where surveys can go wrong. Unit non-response is when an element who's selected for a survey chooses not to respond to the survey. So if we were conducting a stratified sample of elementary students in a city, and we're going to stratify by school, right? We send out our notice that they've been included. Say there are 100 schools in the district, and we sample 20 of them, right? Randomly, and we send out our survey to the 20 that we've selected, and 5 of them say no, we're not going to participate. Now, if those 5 are systematically like the other 15 that do participate, and systematically like the rest of the city, then we actually don't have a problem. We're just reducing our sample size, which increases our sampling error, right? So we just have a little bit more noise in the data. But let's say all those schools are in the rich part of town, and the parents are just like, no, we don't want to be involved in this, right? Then if those schools are all systematically the same, what's going to happen to the inferences we make when we collect that survey? They're going to be biased, right? Because there's a similarity across units that chose not to participate in the survey. A lot of times in our data, there are systematic reasons why people choose not to respond to things. For example, I study police violence, right? And in the United States, statistics on police violence are voluntarily reported by departments to the federal government through the FBI. Now, there's a sort of giant problem with that because a lot of departments don't respond. And I can imagine all kinds of reasons why departments that might be systematically more violent than others might choose not to participate because it would reflect poorly on them, right? So we can imagine theoretically why your location on the quantity of interest, that is how violent are police, would be correlated with whether or not you choose to participate in the survey in the first place. If that's true, my estimate for violence using that data will be too low, too high? What do you think? If all the high violence departments choose not to respond, and then I go ahead and estimate the mean using that data anyway, will my estimate for police violence be too high or too low? It'll be way too low. It'll be negatively biased, right? Because there's a sample selection problem where the departments that have high levels of violence are systematically refusing to participate, right? This is a real problem, right? This is why we don't have good data on police use of force and why we've had to rely on independent sources to generate those data that are not tied to the federal data collection process, because departments can choose not to participate. And there are very clear reasons why departments would choose to participate or not participate based on the levels of violence that that department is engaged in, right? That's unit non-response. If it's random, that is if all departments, just like it got lost in the mail, and that's why they didn't respond, right? And like some of them just didn't ever get the survey, but everyone who got the survey returned it, but like 5% of them didn't, and that's just because it got lost in the mail. That will not systematically bias our inferences. But if people choose not to participate for some systematic reason, that will bias our inferences. And the problem is we don't know. The problem is we very, very rarely know what's actually going on in terms of why we have non-response. We have to use our we have to use our knowledge, and we have to kind of think through the process to make a best guess about it. I'm saying guess a lot in statistics, which might sound weird to you, but there's so much guessing in statistics, right? There's so many assumptions that go into it, right? And that's why, like, just looking, people, I mean, people give like Nate Silver from 538 a ton of flack, but there's this kind of tendency in kind of like data sciencey type fields to just trust the data, right? We have all this data and we can let it speak to us. But the truth is that data come from somewhere, right? And data are produced by some human process. And we have to understand that process really, really intimately in order to make valid guesses about what's going on, right? If you don't understand that process and you don't understand what potential biases may be happening within the data, your guesses can be absolutely incorrect, right? And so that kind of what you could call domain knowledge, right? Or expertise is really essential, right? You need to know where your data come from. You need to know how the process works in order to understand what's going on. You can't just look at the numbers and understand what's going on. There's more to it than that. Okay, item non-response. Let's say the police department gets my survey and they, this is, let's use like, I don't know, whatever. There's a real world survey called LEOCA that asks about a lot of workforce characteristics of police departments. And let's say there is like a officers injured in the line of duty question there, right? And so maybe police agencies all report how many full-time officers do you have? How many part-time officers do you have, right? They report the basics, but some of them systematically don't report about officer injuries, right? They report some of the questions, but not all of the questions. Some of those questions they choose not to fill out. It's item non-response. So unit non-response is I just did not respond to anything. I'm not in the data at all. Item non-response is when some elements of the data are missing, particular elements, right? And we have to be careful about that. Item non-response can be random. Maybe they just skipped that page and didn't see it when they were filling out the survey. Or maybe they chose not to answer that question for some other reason. We have to be really careful in thinking about that. It's often the case that people will choose not to answer a survey question because it may reflect poorly on them or because it makes them uncomfortable, right? And it's often the case that when that happens, the value that they would have reported had they reported it will be correlated with the likelihood that they answer the question in the first place, right? That is, some people will be more likely to answer the question than others based on their characteristics. For example, we know that wealthy people tend to either underreport or fail to disclose their income and assets when asked about them on surveys. So if we use a lot of surveys that ask about household income and wealth, it's likely that those wealthy families may either underreport or choose not to answer those questions, right? There's a lot of other examples about that, right? We could have questions about various undesirable, let's say, substance use and abuse, right? If we were to ask a survey of folks about their substance use and abuse, because we have stigma around substance use and abuse, people may underreport or choose not to answer that question, right? And that could be correlated with problems of addiction, right? So we need to be really careful when we think about missing data. Item non-response can bias our estimates. Unit non-response can bias our estimates. Lying of various sorts can also be a problem, right? I kind of mentioned that here, but my classic example for lying, right, might be the sort of question like, "Are you a racist?" Right? Okay, so like we could ask someone on a survey, "Are you a racist?" And they could say, "Well, no." And just about everyone's going to say, "Well, no." Even hardcore racists will probably say, "Well, no." And there's two ways that can work, right? One could be that they actually truly don't believe that they are, despite meeting some objective criteria we have for classifying someone as holding racist beliefs, right? That person could say, "Well, no," but then in our mind, they should register as definitely hardcore racist, right? But that person may lack the self-awareness to report that truthfully, right? Or may have implicit kind of classifications that kind of lead them to make racist judgments without being fully cognizant of the classifications they're making, right? We'll come back to that in a second, but lying can be a big problem in surveys, and we have to think about that very carefully. Okay, I mean, lying is a strong word, but we could there's deception, and then there's a kind of inability to respond accurately because of individual self-awareness or individual information, right? So there's kind of overt obfuscation or deception, and then there's sometimes people just don't actually know how to respond to a question or don't recognize where they fall on some value, right? Like, it doesn't even have to be lying. Do you have heart disease, right? People who have been diagnosed with it and know they do can report that truthfully. But there are plenty of people who would have undiagnosed heart disease who would say no to that question, but in fact do. And so if we were to just use that answer, we would have a negatively biased proportion of the population that have heart disease. Because what we've measured is people who know they have heart disease, not people who have heart disease, right? And this is these kind of subtle distinctions that I'm going to harp on as we go, but are really critical to making sure that we're describing what we actually know, right? Okay, so unit non-response is when someone doesn't respond to the survey. We need to understand in order to assess the possibility of systematic unit non-response or bias driven by systematic non-response. If we want to understand whether or not there's likely bias in the data, we need to know how the surveys are administered, right? How were they delivered? Who were they mailed to? For example, a lot of political opinion polls are done by done by landline samples, right? Can anyone imagine why a landline sample, that is like someone who actually has like a plug in the wall they plug their phone into, might result in systematically biased estimates for like your attitudes on marijuana legalization? Young people don't have landlines. The only people who have landlines are people who grew up with them, and they skew much older, right? So if you randomly sample landlines, you're going to get an older population. And so your estimates for like marijuana legalization are going to be biased, right? Because we can guess that younger people will be more in favor of it, and younger people also are less likely to have a landline, right? That's been replaced with random digit dialing, right? So now people will just random digit dial, but there's also problems there, right? Because like savvy cell phone users won't answer the phone from an unknown number. The people who are more likely to answer the phone from an unknown number are very likely to be systematically different from the people who won't, right? And that's going to totally structure what we learn from our survey. So we need to think about how these surveys are administered in really technical detail, right? To think about potential sources of bias. Another problem is that response rates have always been low, but they're getting worse, right? And that's because we're getting like flooded with spam calls on our phones, and we're becoming less and less likely to answer random phone calls, right? So response rates for a random digit dial survey may be as low as 1 or 2%. For every 100 calls, you may get 1 or 2 people who pick up, right? Response rates for like email surveys are very rarely higher than 10%, right? So response rates are, because like a lot of times you're like, this is spam, I don't want to pay attention to it, right? Or I get legitimate surveys all the time. I'm like, this is going to take me 20 minutes to fill out. I don't have 20 minutes to do this right now. Trash, right? So we have all these demands on our time. Response rates, though, are typically very, very low. And so if that's random, that's okay. But if it's non-random for any reason, our inferences can be biased. And we need to be really careful about that, especially when response rates are so low, right? That the bias can kind of be magnified in the context when response rates are low. We can talk kind of mathematically about why that would happen, but we can end up with a really weird subset of the population, and it can very dramatically skew what we're seeing. So completely random non-response does not bias inference, but any kind of structural direction, when I say structural, I mean there's a pattern to it. Any kind of pattern in who is taking the survey and who is not taking the survey can totally screw it up, right? And this is one reason to be deeply, deeply, deeply skeptical of political polling, right? Is that these problems are endemic in political polling. Most, like the census and other organizations, actually go knock on doors, and that has much, much higher response rates. And then we also can know which houses didn't respond, right? And we can use things we know about those places to weight our sample in various ways to try and correct for that non-response. So census and other organizations that put a lot of time and energy into this do a pretty good job. And a lot of the surveys that we typically use in social science do a pretty good job, but political opinion polls conducted by ABC News are typically not so carefully done. Okay. So non-response would be an issue when there's a structural pattern to non-response. We'll do question non-response, and then we'll take 5. So question non-response again, or item non-response. So when an individual takes the survey but refuses to answer or skips a particular question. This might occur if a question makes an individual uncomfortable. If, for example, maybe I'm being interviewed as part of my survey. I have a survey taker who's talking to me, and they're like, okay, describe your medical history. And let's say I have a history of mental illness and don't feel comfortable disclosing that to the stranger, right? Then I'm just going to say, I'd rather not answer that question, right? And so there might be a pattern to where we have social pressures around, or social stigmas around particular things that might make people uncomfortable answering them on surveys, and they might choose to skip them. Okay? There could be all kinds of reasons for item non-response, though, right? That's just one, is a kind of stigma, but there could be all kinds of other reasons why people might choose not to answer questions. And when the choice to not answer something is correlated with the truth, that is, my decision to answer or not answer this question is a function of my value on that question, my mental health status, right? My decision to answer or not answer that question then is correlated with my missingness. And when we have that, we have bias. That's a big problem. Okay. We just talked about social desirability bias. This is my favorite. What kind of crimes do you like to do? Right? You go ask someone that on a survey. Are you going to get the truth? Probably not. Right? So we have to be super careful with how we ask survey questions and how we use survey data, right? Because we're typically using it to learn about mu, to learn about our population parameter, our population parameter of interest. And if we don't think carefully about where the data came from, we can be wildly off with computing our sample statistics from our observed data, right? That idea of social desirability bias in particular is when, for example, a survey taker believes that someone they're interacting with will view them favorably or unfavorably based on their response to a question. Are you a racist? No, right? We have a strong stigma. Maybe it's weakened, but in theory, we have a strong stigma against racism in our society. So people don't feel comfortable identifying themselves as racists, right? Despite the fact that they may hold racist views or take part in racist activities, right? We have a strong social system that penalizes involvement in crime, right? So asking people directly about criminal activity involvement, right, actually carries legal risks right? These people are like, hell no, I'm not going to tell you what I do in my free time if it carries risk of arrest, right? And so that is going to lead to a bias, a systematic bias in their responses based on social perceptions, right? Because humans kind of structure our communication based on who we're talking to, right? And based on our perceptions of what the impact of that communication will be. Which is why when we're doing statistics, we still have to think about like human psychology, right? And communication and all these other complex things that produce the data, produce the numbers that we're working with. Yeah. There's a lot of process. Professor Apel and I were just talking about this with the uniform crime reports this morning, right? In order for the uniform crime reports, which is what we use to like, there's been a lot of discussion about increasing crime rates across the country based on these data, but these data are voluntarily reported by police departments based on crimes that get reported to the police, right? So we have to think about, okay, what crimes get reported to the police and which don't? Well, first, what gets called a crime and what doesn't, right? Then what gets reported to the police, then which police agencies choose to report to the federal government. There's a lot of process in there and a lot of places where bias could affect our estimates, right? And so we have to be super careful when we think about this stuff. Let's take 5 and then we'll come back and keep going on this. So let's look at non-response and a survey of exposure to violence in Afghanistan. So this is a survey conducted by some American political scientists in the early parts of the war in Afghanistan about exposure to violence from either the US-led coalition forces or from the Taliban, and attitudes about the US-led coalition forces. And the goal here was to try and understand how exposure to violence from both sides of a conflict impacts civilian attitudes toward the occupying force, right? So the goal, so this is an incredibly difficult survey to administer. We can imagine all kinds of reasons why we might have problems with unit and item non-response in this kind of survey, right? Because responding to a survey of this sort could actually be putting someone's life in jeopardy if they're fearful that like someone from either side might react negatively if they hear the wrong answer to a question, right? So let's look at non-response. This is so this is a place where non-response almost certainly is going to be associated with a bias, right? Oops, that's not easy to read, but it's in the slides. Screen at that so you can see the URLs. But if you have the R Markdown file, you can access the data using these URLs. So we're going to read them off of Imai, who's the textbook author's GitHub page for the software. Right, and so let's look at those data sets real quick. We have 2 data sets that we're going to look at. Afghan is the individual survey responses. I'll use Glimpse just so we can see it a little more clearly here. So here we have our variables: province, district, village, ID. So we have a stratified sample, stratified by province, district, and village. So we're going to have a survey where we randomly select, well, no, I think they deliberately select provinces based on exposure to conflict, but then randomly sample districts within those provinces and randomly sample villages within the districts. And so these are kind of identifiers for our sampling units. Which province are we talking about? Which district within the province are we talking about? And then which village within the district are we talking about? And each village in the data set has a unique identifier, right? And is anonymized, right, to protect respondents, right? And then the districts and provinces are identified. And then we have data on individual measures. So these are things that the survey respondents answer. We have age. I believe this is a survey of only men. Age, number of years of formal education received, whether the person is employed, what's their income range, whether they have a violent experience, whether they have been exposed to violence from the coalition forces, whether they have been exposed to violence from the Taliban, and then their response to a survey that they constructed to assess attitudes toward the coalition that kind of has a complex design that allows people to kind of answer in code to what their attitudes about the coalition forces are without directly revealing the truth. So the researchers here use a very clever design that we won't get into that allows people in theory to answer the question, do you support the coalition forces, without directly answering that question, right? So the idea here is to protect people from exposure to violence for participation in the survey. How this cleared IRB, I don't know, but because you're actually putting people's lives in jeopardy by running this, right? But nonetheless, it's an interesting case to think through. We could think about the ethics of doing this kind of work for a research design course, right? If I were sitting on IRB, I'd almost certainly not approve this kind of research, but that's me, because people are putting their lives on the line to answer, and it's not just your response that's endangering you; it's your participation that's endangering you, right? If, for example, members of the Taliban see you talking to white researchers about your attitudes toward the coalition. Anyway, all of this, are the variables included, right? Research ethics, of course, is a very complicated and broad area that we could work in. Questions about the basic structure of the data that we're looking at here? No? Okay. And the URL is still cut off. Oh, right. We have a second data frame that's the Afghan village that gives us some characteristics of the villages. So it tells us the altitude, which, because Afghanistan is particularly mountainous, right? We might think that those villages at higher altitudes might be more remote and might be systematically different from places that are at lower, closer to sea level. We have the population of the village, and we have whether they were sampled. Village surveyed is an indicator for whether the village was included in the data set or not, whether they were included in the sample. And this should theoretically be random. So let's look at that. Actually, all we're going to look at here for now is the village surveyed question. So here are the included provinces. Here are the included districts within those provinces. This is just describing the data. I'm kind of walking you through, when I look at a new data set, these are the things I do, right? I want to understand what I'm looking at. So I'm going to run descriptive tables of the categorical variables. I'm going to run histograms of the continuous variables, just so I can kind of get a feel for what I'm looking at, right? You need to, before you start asking complicated questions of a data set, you need to really kind of get your head into it and think about what am I looking at. So running descriptive tables, running histograms, running simple visuals is a great way to do that. Let's explore the distribution of age, right? So what do we see about this age distribution? This is a histogram of age in the data set. Someone describe what's going on here. It skews young. Yeah. So the peak is under 20, right? So the most frequent age in the category, the modal age, mode is kind of the peak of the distribution, the highest, the most frequent response, right? It's kind of in the, like, let's say 15 to 18 range, right? But then we have a ton of data between that 15 and maybe let's call this like 30, right? So this band here has a whole lot of our data in it. And what do we see as we go? Very few older people in our data set. Now, there could be two things going on there, right? One, there could just be fewer older people. Life expectancy is quite low in Afghanistan because you're talking about a place that has been enduring, 50 plus years of war, right? So the life expectancies are quite low. And access to medical care might be quite difficult. So we might have multiple reasons why life expectancy would be suppressed. So we don't have a lot of older people here, mostly young. Might also be that older people who do live there might choose not to participate, might be more skeptical of the project and might choose not to participate. So we could have both the objective age distribution the true age distribution of the population of interest could be this, or our observed age distribution could be biased from the true age distribution of the population of interest. We don't know, right? Reason to suspect both things could be going on. Or it could be that young people were systematically less likely to participate because they were more fearful of retribution, right? And so it actually could be that the age distribution could be more peaked, right, for young people if that process was going on. We don't know, right? So that's one reason we need to understand where the data comes from really carefully before we start to make any judgments about age. We want to see this distribution, and maybe we like have a census of these districts that we can compare it to say, okay, does this distribution match on to other data that I've seen that describe the age distribution of these places too? If it does, then we might be like, okay, maybe whatever error we have here is random. It doesn't appear to be systematically different from things that are similar. But this is where data visuals and what I might call triangulation, that is kind of thinking about other external data that we could look at to think about validating what we're seeing, right? So maybe we have other places we could look at the age distribution of the country to think about whether we think this is valid. Yeah. Okay, but a histogram is the way to look at it, right? Histogram is the perfect way to look at the distribution of a continuous variable like age. We get a really good sense of what's going on here. And this picture tells us a lot. Tons of young people, very few older people. Okay, this is education years. Again, now I'm going to show it as a bar plot because it's a discrete variable, right? It doesn't have as many categories. Age in this data set goes from like 12 to 80. We're going to treat that as continuous. Education years only goes from like 0 to 16. We're going to treat that as discrete, right? So there's no decimal, there's no continuous range here. So what do we see here? Education years is a bar plot. X is the number of years of education, and the number of respondents in each category is the height of the bar. What do we see?
People that are, there's not a lot of variation.
An overwhelming majority of the sample, well, yeah. So we're at like 1,700 or so respondents report having no years of formal education, no formal years of schooling, never having been to school, right? With a very small number, we could think of 12, right, as typically being the high school education level. 12 years is typically what we would call the high school education level. So we have, 270 or so respondents that report having at least 12 years of education. Very few report post-secondary education. That is college or higher, any college or higher, right? We have a handful that report a couple years in college. These would be our college graduates at 16 years. And these would be our people that have some graduate training, right? Once we get above 16. So this distribution appears overwhelmingly to be composed of people that have no formal education. I would hesitate to say uneducated because of course they know quite a lot, right? But they haven't necessarily been through the formal education system. They haven't had access to formal education. So now let's look at employment. Right, I'm just kind of working through all the variables in the data set and designing visuals that help me understand what's going on. Employed, that's a binary, so I just want to look at a table. We have 1,600 employed, 1,100 unemployed. So the majority are employed, right? But plenty of people who are unemployed, right? If we were to use this to compute accrued unemployment rate, right, we could just divide 1149 over 1149 plus 1605. And I don't know, we get like a 30% unemployment rate or something like that, 30 or 40%. Okay, next here's our income. And again, this is categorical, right? We saw that it was reported as ranges. So we're just gonna do a frequency table to look at how many are in each category. We could do a bar plot here too, that would work fine. R doesn't really understand. These do have an order to them, right? This goes first, this goes second, this goes third, this goes fourth, this goes fifth. R doesn't really understand that because it's a character, right? So it's actually just going to alphabetize it, where 1 comes first, 2 comes second, right? This has a 3, where this has a 1, right? And then the alphabetical comes last. This is where a factor can be useful in R, is then we can tell R what the actual order for our categorical variable is. Right now it's stored as a character, so R doesn't understand it. If we treat it as a factor, we can say, no, R, this is 1, this is 2, this is 3, this is 4, this is 5, and it'll structure our output in that order. That's when factors are useful, right? We talked about factors a little bit in the homework assignments, but I didn't actually introduce them to you at all. It's because their utility is actually really limited. I find them to be only useful in the case of visual design, right? When I need to like make a plot where a categorical is in a particular order, that's the only time I use factors in my work. I don't use them in any other circumstance. But they are useful for this, right? I'm not going to show you how to do it now because it's complex and not that handy. But, oh, right, I do it here. I'm an idiot. Sorry. I like anticipate things. I haven't taught this in a year, and I'm like, okay, well, here we go. So we can reorder it, factor. We can mutate income as a factor for the levels, and then I provide them in the sequential order that I want them to be in. And now R will understand that they should go in that order. Sorry, bit brain dead these days. I won't complain about sleep deprivation today. No, I will. I just did. I'm sleep deprived. It's true. It's true. It's been like 2 weeks since you've heard me complain about never sleeping because my 3-year-old is a tyrant. My 3-year-old is a tyrant, and she's lovely, but she never lets me sleep. Okay, so let's reduce this to a few variables, and then let's reduce it to only our continuous variables, and then run a summary table. So I'm going to take our Afghan data. I'm going to select these 3 variables, and then I'm going to run the summary function over each of them, right? And so I'll get the ranges, I'll get the means, the medians. I'll also see how many missing values I have. And these are perhaps unsurprising. Now, just eyeballing this, what do we see? In the missings, I see exactly what I would expect to see. Why is that? What do we see going on here? There are twice as many people who did not answer, were you exposed to violence at the hands of the Taliban, than answered, were you exposed to violence at the hands of the coalition forces? No one really was worried about answering employment. But this appears to be a problem, right? We have twice as many cases who didn't answer this question as answered this question. And there's strong reason to suspect the reason people didn't answer this question is because they were fearful of retribution, right? If that's the case, then our mean here, if not answering this question is associated with 1, is this mean too high or too low? It's actually going to be too low. Because we can probably, let's assume that all the 54s were actually 1s, right? If we make the assumption that everyone who did not answer the question was indeed exposed to violence at the hands of the Taliban, but were fearful to say so, then we would have 54 more 1s in this category, and this mean would go up. So there's strong reason to suspect here. Similarly here, we could probably assume that the people who didn't answer were fearful to answer, yes, I've been exposed to violence at the hands of the coalition. And so we can also assume that this might be higher, right? But in this case, our estimates, our statistics are going to be negatively biased relative to the parameter of interest, relative to the truth that we want to learn about. What proportion of this sample has been exposed to violence at the hands of the Taliban? What proportion of the sample has been exposed to violence at the hands of the coalition forces? There's reason to suspect that this number might be too low. And there's reason to suspect this number might be too low as well, right? Particularly if there's a coalition aligned surveyor asking respondents, has my team injured or harmed you or your family in any way, right? We can suspect there might be reason to say no. That would be a social desirability bias, right? Okay, so without actually like going too far, just knowing some basics about the study design and looking at a simple table, we can already make a pretty good guess that these answers may have a bias, that our statistics may have a bias to them. Yeah. I'm not saying for sure they do or they don't. I don't know for sure if they do or they don't. but I have strong theoretical reason to suspect that it might be there. And then it would be on the researcher to demonstrate you're right to anticipate that. Here's why I do think there's a bias, or here's why I don't think there's a bias. Or here's how bad I think the bias is, right? Yeah.
What's the sample size for these variables?
We have a sample of, I think it's about 1,600 or so. No, it's 2,700.
54 out of 2700.
That's relatively low. So we can ask what share of the sample is missing, right? If we have 54 over 2,700, right, that's a relatively low proportion of the sample. What is that exactly? 2% missing, right? That is pretty low. And typically, we might think of that as, okay, so what's the magnitude of my possible bias if 2% of the cases are missing? Well, we could just do an exercise where we say, well, let's assume they were all 1, and then recompute things and see how much higher our estimate would have been. And if item non-response is the only source of bias, then I know the magnitude of my possible bias, right? The magnitude of my possible bias would be, what is the maximum amount this mean could increase by if all of these were indeed 1s? Or if all of these were indeed 0s? Then I have some bounds I can put on the possible range of the truth, right? And that's one way as a researcher to be honest about your data and to be transparent with your readers about where the possible range of the truth is, right? Our goal in statistics is never to demonstrate too much certainty. We always want to be painfully honest about how uncertain we are about things, right? You never want to err on the side of being too confident in your numbers. You always want to err on the side of demonstrating how much uncertainty you have about what you're reporting, right? We are very conservative in statistics in terms of how much faith we put in something, right? How much faith we put in a number. Our practice, our kind of goal as practitioners of applied statistics should be to be very honest about how much uncertainty we have and to always err on the side of more uncertainty rather than less as we report things, right? The danger of being overconfident is almost always greater than the danger of being underconfident. Okay, so here's the variables in the Afghan village. After I'm gonna like harp on that as we go, and it's one of those things that's like not totally intuitive until you start doing this stuff a lot, but it's really important to always kind of err on the side of not trusting your data as much as you might like to, right? So always assume that there might be something going on that you don't understand or something going on that might bias things, right? Okay, so here's the Afghan village data. We have altitude, population, and then again, whether the village was surveyed. So let's look at those variables real quick. Here's the altitude variable, right? We have, what do we see going on here? How many villages are at sea level? 2. How many villages are on top of high mountains? I think this is measured in meters. So we don't have a whole lot of villages at 3,500 meters. Most of them are in this 2,000 and 1,000 range. I would call this a bimodal distribution, meaning we have kind of 2 peaks, right? It's not like our age distribution really just had 1 peak, right? Kind of goes up and then down. Here, much like the country, we kind of go up and then up and then up, right? So we have a lot of people living in like lowlands and valleys, fewer people there, a lot of people living in highlands. Right? Okay. So that's our altitude histogram, right? But a histogram tells us so much more than just like looking at the average of altitude, right? This histogram really tells us who's in the sample, which villages are in the sample. Here is population. What does this one show us? Describe this distribution. It's weird. Not particularly informative, but I like it. I like it. What do we see? Most of the villages are, population is our X, most of the villages are small, right? The overwhelming majority of these villages are very small. We have a few kind of in the city range. One with a population over 30,000, maybe three with a population between 20 and 30,000. A handful with a population over 5,000, right, in this range. Most of them have a population of less than 5,000. I would call this a heavily left skewed distribution, right? Meaning it's clumped up towards zero. Just about all of the mass of the distribution, meaning most of the cases in the data are close to zero, right? Very peaked at zero and then declines rapidly. Population, like some other things, if we're trying to estimate a linear relationship, this is where that logarithmic function could come in really handy to transform this into a more linear distribution, a smoother distribution, one that has less of a peak. But we're not going to worry about that for now. We'll talk about that later. Oh, see what I do? I'm just like anticipating the things that past me already did because sleep deprivation screws up your memory. Okay, so that's like 3 minutes of complaining today. Am I good? I hit my quota? Okay. Sorry, I complain too much. Here's what the log transformation looks like. And we take this skewed variable, and all of a sudden the distribution looks kind of like a normal distribution. That's what log transformations do to exponential functions, right? Is they transform them into approximately normal distributions. So exponential distributions, we can typically apply a logarithm to them and then get them looking kind of normal. Why we would want to do that is a topic for another day. When we get to regression, we'll see why this is something desirable to do. But a lot of times we want to have variables that are approximately normal because we're going to make a lot of assumptions about how errors work. And the assumption we're typically going to make is that those errors are normal, right? In order for our math to work. So the log function will come in really handy later. But it's basically doing the same thing. It's saying there's basically no villages at zero, right? And then we have a lot in this range where, like, let's take the log of like 6 seems to be the peak, right? The mean value. So we have a lot of villages with about 400 people. Right, we'll exponentiate that because what we're looking at is the log. So to invert the logarithm of population, we just exponentiate it. So we take e to the power 6 and we get 403. Right, so what this is showing us is that the peak, the modal category is 403, right? Or the median of the log is 403. The median of the population is about 403. Median of the log is 6, sorry. Okay, anyway. The average village has, so of all the villages included in the data, which again is a list of all villages in the included provinces and districts, right? About 11% of those were surveyed. 10.9% of those villages were surveyed. So 89% were not. So in order for this to be a simple random sample, each village had to have about an 11% chance of being included in the survey. Let's see if the sampling is representative of villages. We'll just look at that plot while we wait. Okay, so here is altitude. I'm doing a box plot of altitude by whether the village was included in the survey. Remember a box plot, we're going to see the mean here, the interquartile range here, the 75th and 25th, and then the 95th with the bars. Oh, good. Sorry. I'll upload the corrected slides when I'm done. So what do we see here? Do we think that altitude is related to whether the village was included in the sample or not. So we don't see any systematic difference here between places at high altitude or low altitude with their likelihood of inclusion in the sample, which is good, right? We don't want to see systematic differences here. We can imagine a survey where like, oh, that village is up in the mountains, I don't want to mess with it, right? And we only take those ones that are easier to access, right? And that would definitely affect our data. But in this case, we don't have reason to suspect that altitude impacts whether villages were included or excluded in the sample. Right? Again, these are the kind of quality checks that honestly I want you to do when you're working with real world data, right? To think about sources of bias and to really push on your data to investigate potential sources of bias. Right? Because at the end of the day, when you report statistical results, that's on you, right? And it's on you to have done your due diligence to ensure that you are reporting to the best of your ability what you believe to be accurate. Okay, sampling representative villages by population. Let's look at that. So this is the same plot, but now we have population on the Y instead of altitude. And I've done it as a logarithm just to smooth out those distributions a little bit. Otherwise, it'd be a little difficult to look at because these boxes would just be at the bottom and we wouldn't really be able to see anything. What do we think? Are the villages included systematically different from the villages not included by population? Or are they similar? They look similar to me. Right, we're going to have more outliers here just because there's many more villages excluded. There's 90% of this data here and only 10% of the data here. So we can expect that to be wider, right? Just because there are extremes in this distribution, right? But the mean is about the same. Interquartile ranges are similar. Looks fine to me. Here, when we're looking at kind of comparing for systematic bias, we really want to focus on measures of central tendency. That is measures like the mean and the median, right? Because a bias is going to pull the mean or the median in one direction or another, right? We're looking for, is that mean off center from where across the two groups? Are the means in very different places? If they are, that should raise red flags, right? We expect the measures of variance, especially if the sample, if it's different. Here we know we have 90% and 10% of the cases. We're going to have more spread when we have more cases if we have a measure that has a lot of spread to it, like population does, right? The range of that is 0 to 30,000. If we're only taking 10% and there's only one 30,000 case, we're very unlikely to get that 30,000 case in our 10% bucket. We're very likely to get it in our 90% bucket, right? Just by virtue of how big the sample is. Okay, so I still didn't fit it on the screen, but I'm just going to proceed as if I did. Okay, so we're good there. So here's another way to look at it. Instead of looking at the box plot, we could facet histograms. And actually, this would be my preferred approach because this will really let us zoom in on details of the distributions. And so here, I'm going to do the log population. I'm going to plot a histogram with a geom histogram. And I'm going to facet wrap by whether the village was surveyed. So I'm going to produce one histogram for village not surveyed, one histogram for village surveyed. And I'm going to add this argument scales equals free because I want the y-axis to not be constrained. Because if I made them have the same y-axis here, this would go up to 250, but there's 10% of the cases here and 90% of the cases here. So we expect this distribution to be shorter, right? Noted here, this goes up to 25, this goes up to 250. So it's just an order of magnitude difference, right? It's 10 times smaller, which we expect to see anyway, right? So scales equals free just says, you know, let your axes be whatever you see in the data and fit it to that plot rather than holding it fixed. Fixed scales would mean we have them on the exact same. Let's show you what that would look like. Easier to see than to explain. Right, that's with free scales. That's with fixed scales. right? And we can see that our y-axis here goes up to 250, but our peak on our one plot is only 25, right? Now, maybe this is useful, right, for telling us, oh, there's so many fewer cases over here that are over here. But if we already know that, and we want to compare shapes, right? If we just want to compare shapes of the distributions in terms of proportions, right, then allowing the scales to be free is really useful. Okay, so what do we see here? I see no problem. Similar to the box plot, these distributions look like they have a very similar shape, right? They peak around 6, right? They're pretty much symmetric, meaning their tails on the right and left-hand side are similar, right? They're about as high over here as they are over here. They go for about as far on both sides. So a symmetric distribution would have the same shape on both sides, like similar left and right-hand tails. The peaks occur at similar places. These look very similar to me. I don't see a problem. Of course, we're going to see small differences, and you're going to develop an eye for like what could be random, what could be systematic, as you just kind of do this more and more, right? It's a bit of a craft in terms of making judgments based on visuals, but I find it to be a lot easier personally to work with something like this than just comparing means, right? Because I get a sense of both spread and centrality. Okay, and let's say item non-response by region, right? Perhaps the Taliban has more power in certain places than others. And it's in those places where the Taliban has, let's assume that their presence is a function of region and their power is a function of region. So fear for retaliation may be a function of region, right? So item non-response may be a function of region. What do we see going on here? See, in Helmand province, we have about 3% of the data missing. But then when we look at Uruzgan province, and we have 6% of the respondents, more than 6%, chose not to answer the question about exposure to Taliban violence, right? And about 2% of the sample chose not to respond to questions about coalition violence. Logar province and Kunar province, we have no missing data at all. People did not appear to be fearful of retaliation in these places. Khost province, pretty low, but in Helmand and Uruzgan province, we have a problem. It appears that non-response is a function of place. That respondents in certain regions are more likely to answer the question than they are in other places. And if there's systematic differences of who lives here or what's going on here and here compared to here and here, our inferences will be biased. Right? So this is the kind of exploratory data analysis that good training and data visualization will help you do and help you sniff out problems in your data, right? Kind of you're being a bit of a detective, right? And you want to just kind of think of all the ways, all the relationships that could be occurring in this data and go through and map them out, right? And think about what might be going on. Okay, so that plot is just a bar plot faceted by region, right? Similar to here, I faceted by village surveyed. Here I facet by a categorical variable, like 1, 2, 3, 4, 5 plots, right? This is called a small multiples approach, where we get small plots and multiple versions of the same plot to help us compare across groups, right? It's a really, really powerful technique for data visualization. Okay, so in summary, unit non-responses can bias survey estimates, right? I hope I've hammered that home, right? Missing data can bias your estimates. Item non-response can bias survey estimates. Social desirability bias can bias survey estimates. Errors induced by these biases can lead to incorrect conclusions. See the consensus that Trump was going to profoundly lose the 2016 election, right? The polls had him at like a 99% chance of losing that election. When indeed on election day came, we could debate about fairness, but the results did not go in that direction in 2016, right? These kinds of biases can have profound real world consequences in terms of our ability to make inferences about something we want to know about. Okay, now we're gonna do some data visualization exercises. So here I want you to be coding along with me. We're going to return back to the IPV data that we used as an example before, the Internet Partner Violence Survey. I'm sorry, that path is not going to be valid for you. Let me get the right path. Do y'all have that data? Did I post it on Slack last time? I think I did, but here, I'll find it. I've got it. I'll just post it on Slack. That'll be easier. Actually, I probably have it on my GitHub. Sorry, this is taking me a second. Sorry, y'all. Okay. So, now that data is on the internet. Okay. I'm posting the URL there. And in order to pull that data into your, let's make a new R script. We'll just do a library tidyverse and read CSV to that URL. So you can just copy and paste that URL from Slack. Just right click it or right click, copy link. Then go here, read CSV, and make sure to wrap the URL in quotation marks. And then read it in. Oh, I should probably assign it somewhere. It's called IPV. Stored in a data frame. Okay. Give y'all a second to load that in. Anyone having challenges with getting it? Okay, we good to proceed? Anyone need more time? Okay, cool. So we have the data loaded in. Now, again, let's just take a look at it. Just to make sure it read in correctly. We've seen this data before, so we won't go into too much detail, but I just want to ensure that it loaded in the way I expect it to load in. So I'll use head to do that, right? And the data looks fine. Sometimes you might get a corrupted file or something, so you always want to check that. Just make sure the data is how you expect it to be. Okay, so we talked last time about how we could look at bivariate relationships. And the best visual to look at bivariate relationships between two continuous measures is a scatter plot, right? Where we put one variable on the x-axis, one variable on the y-axis, and each point has a unique location defined by its value for secondary schooling and its value for the no media survey response, right? That is women in the country reporting they had regular access or no access to media. And then we can assign a color equal to region here, where we can then kind of add an additional aesthetic to it to sort out visually where each region of the included countries are on this scatter plot. So we actually have how many variables displayed here? What's that? We have 1, 2, 3, right? And we can see that in our aesthetic call, X, Y, color, 3 variables. We actually have a trivariate relationship going on in this plot. Once we get past 2, we usually just say multi, right? So we call it a multivariate plot. So let's ask now with a time series plot, this is a line plot. When we have something that's a function of time, often what we're going to want to do is make a line plot out of it rather than a scatter plot out of it. A line plot or a time series plot, when the line has time on the x-axis, we call it a time series. That is, it's a repeated measurement of something over time, as in longitudinal data. We'll put time on the x-axis. In this case, that's year, right? So we want to look at things as they change, moving forward in time. We're going to put the secondary schooling variable on the y-axis. And then we're going to make region, again, color. So this is telling us something different, right? This is giving us a very different set of information than this plot, right? Where we're just looking at the correlation of these 2 variables where the secondary schooling occurs. And what will we describe? Sorry, let's kind of move back to our scatter plot for a second. What do we see going on here? Ignore region, because that's a little difficult to read, but what do we see going on between no media and secondary school? Pretty tight relationship, right? So for places with high levels of women's secondary schooling, they tend to have what kind of levels of media exposure? Tend to have low values for the no media question, meaning high values of media exposure, right? So we could say that as secondary schooling increases, women tend to have higher levels of exposure to media. As secondary schooling decreases, we tend to have lower levels of exposure to media, although we do have quite a bit of spread here, right? There's some heterogeneity there. Heterogeneity just means there's differences within that group, right? So this group of observations of countries with low levels of secondary schooling for women, we have a lot of spread for media exposure. But they tend to be lower than they do over here. We can imagine drawing a line that goes down through this plot, right? I would call that a negative association. There's a negative association between women's secondary schooling and no exposure to media, which is a weird double negative. But like, right, we can call it a positive association between secondary schooling and exposure to media. Okay. Here, we can ask a kind of question about like a kind of international development perspective, right? We might expect that exposure to secondary schooling for women would increase over time. And what do we see in the countries included here? We actually don't see a clear increase over time on the sampled countries, right? So looking at this, right, there's going to be some sampling error, right? Because the number of countries sampled is relatively small. The number of countries in the world is relatively small, right? So we're going to just get random fluctuations, these kind of zigzags. Do not interpret those zigzags as like, well, it went up, then it went down, then it went up, then it went down. That's what error looks like, right? That's just what noise looks like. Noise looks like random fluctuations around a central line, right? So this kind of bouncing up and down that we see in the red line, that's just noise, right? At least I'm guessing it's just noise, right? That's what noise tends to look like. Noise over time tends to just look like static, right? Bouncing up and down. Where we get worried is if it's consistently higher, right? If those points are consistently above where we expect them to be, or consistently below where we expect them to be. Or in this case, we maybe see a slight, if we were to average through this line, maybe we see a slight upward trajectory, right? If we were to just kind of draw a line straight to the middle of all those points, maybe it's increasing slightly over time, but there's still noise bouncing around it. We'll look at a lot more time series plots, and we can talk about this problem of kind of moving averages as we keep going. But we see not a really clear trend here across regions in terms of increasing secondary schooling like we might expect, right? Now, correlation. So a kind of new stats concept I want to introduce. When we talk about an association between two things, as we did here, we're effectively talking about a correlation. A correlation is a numeric measure of the strength of an association between two variables. So a correlation tells us how much information do we get about variable y by knowing the location of variable x if x and y have a linear relationship. So effectively, we're saying, if I know x, what do I learn about y? Assuming a linear relationship between the two variables. Correlation of 0 looks like this. So these are data I simulated using two correlated variables, right? And in this case, the correlation between those two variables is 0. Knowing information about x tells me absolutely nothing about y, right? As I move along x from -3 to +3, I see values of y that are equally dispersed at all values of x. The cloud of points around the horizontal line, right, is about as wide at every single part of the x-axis, right? That cloud, right, is kind of similar in shape all the way across. That's evidence of no correlation when we look at a scatter plot. This seems archaic, but like you're going to look at a ton of scatter plots, and eyeballing the strength of an association on a scatter plot will become a really valuable tool. Right? There's actually like a, I don't know, it was stupid, but like there's an online quiz that was like, guess the correlation coefficient, right? Where you just like look at a scatter plot and guess it. I've gotten pretty good at it. Where I'm like, I could get it most of the time within like, you know, a point or two. But okay, this is what a 0.1 correlation looks like. Eyeballing this, I would have a really hard time distinguishing between this and this, right? The computer can estimate it, right? But here, the strength of the correlation, that is technically an increase in V1 of 1 unit is associated with a 0.1 increase of V2. That's technically what we're saying. We could think of this as a slope, right? So this is effectively a slope. 0.2, we're starting to see a little more structure here. As the values on x are lower, the values on y tend to be a little bit lower, and as the values of x are higher, the values of y tend to be a little bit higher. But you can see as our correlation coefficient increases to 0.6, we're starting to see some real structure here, right? For low values of x, we have systematically lower values of y. For high values of x, we tend to have higher values of y. And as our correlation coefficient increases, the distance between the line x equals y decreases, right? So they become more and more compactly distributed around a central line as my correlation coefficient increases, to the point when I have a correlation coefficient of 1, all the points fall exactly on the line x equals y. If we know X, we know Y with certainty. Here, if we know X, we know Y with a pretty high degree of confidence. If I know that X is equal to 2, I am very certain that Y will not be equal to like -2. I don't know for sure it's going to be equal to 2, but I would bet that it's going to be, somewhere between 1 and 3 if I know that X equals 2. But when the correlation is 0.2, right, if I know that X is equal to 2, right, Y could be just about anywhere. I don't have a lot of faith about why. I don't have a lot more information about where Y is going to be based on my knowledge of where X is. If the correlation is 1, that means the two variables are identical. Knowing one provides me exact information about the other. Okay, so this is the correlation coefficient. It can take on values from -1 to 1. So obviously, if we can just kind of inverse this, flip it, right, the line would go the opposite way if we had a negative correlation coefficient, right? As we kind of observed here, a negative line that we can imagine going through here, right? Eyeballing this, I would call this a correlation of about a 0.3, a 0.4, and it's negative, right? And it does kind of look like maybe this range, right? In terms of how strongly those points are adhering to an imagined line. Typically in the social sciences, we see correlations in this like 0.2 to 0.5 range. Most of the phenomenon we're looking at fall in that range. They tend to not be anywhere close to these ranges. In the physical sciences, you'll see stuff down here, but in the natural sciences, we rarely do. The reason for that is that human processes are always multi-causal, right? Is that they're always very complex patterns of causation that drive any social process. So knowing one thing is almost never going to give us perfect information about a human outcome, right? In order to get perfect information about a human outcome, we would need to know many, many, many things. And even then it would be imperfect because at the end of the day, humans make choices, right? We have agency. So, it's not like we don't have a full structural determinism, right? Where if we had perfect information, I know exactly how everyone will behave in history, right? We don't live in that kind of world. There's always randomness in the system. We could call that entropy, or we could call it agency. We could call it whatever we want, but we can never perfectly predict human behavior. Okay, so again, this is just kind of putting those imaginary lines onto it, right? And I'm using the geom smooth function in ggplot to do that. We'll kind of work through that in a moment. But you can see here, the imagined slope of our zero line, of our zero correlation is 0, right? The slope of the relationship between X and Y is 0. Here, the slope of the relationship between X and Y is 0.1, 0.2, etc. Right? The slope increases up to a maximum of 1 as our correlation coefficient increases. Yeah? Cool. So we can kind of see how that slope quantity relates to our correlation coefficient pretty directly. Feeling good about correlations? Okay. I'm not going to show you how to compute them because you're never going to need to do it on your own. But in R, you can use the function COR to compute the correlation coefficient. Okay, so we're going to do a little bit of math because I want you to understand what a z-score is. And we need to understand this conceptually to kind of think about scaling variables. We already talked about this a little bit when we talked about comparing the standard deviation of a quantity to its sample average, right? So for example, in homework 4, right, you compared the test score of the treated and untreated against the standard deviation of the test scores in the treated and untreated groups. Implicitly, what I was asking you to do there was to think about a z-score. So a z-score is a typical tool that we'll use to transform variables to be comparable to each other. And the way we'll do that is we'll put them on a standard deviation scale. We'll put them on the scale of their own variation, right? So what we're going to do is we're going to take our observed variable x, or observed value for x, subtract the mean from it. So we're going to take, in this case, let's say the mean here of all of these variables is constrained to be 0, right? I defined the mean to be 0, and they're kind of spread around 0. So xi in this case is about what? Well, so let's look at, I guess we're looking at y there. Let's look at this dot, okay? The x value for this dot is about 2.5. The average for X is 0, right? So in the numerator here, we would have 2.5 minus 0. So that would tell us how far away is this observation from the mean. It's 2.5 away from the mean. What's the standard deviation of all observations within that variable? In this case, I've constrained it to be 1, right? These are draws from a normal distribution with mean 0, standard deviation 1, but that's going to be something we compute from the data. So in this case, I have 2.5 minus 0 over 1. So my z-score will be 2.5. In this case, it'll be identical because I've used the normal 0, 1. But effectively, what we're doing is we're trying to get things into that scale. So on our test score variable, let's say that we had I'm going to leap ahead a little bit with my notation here because it just is easier and I might as well introduce it now. But let's say that we do actually have small differences in the treatment group and the control group on our test scores, right? So let's say we have score of treated. I'm going to use this symbol to indicate is randomly distributed. So the tilde in our mathematical notation is going to indicate here follows the probability distribution. Follows a normal probability distribution. I can define lots of different kinds of probability distributions. Here I'm going to use a normal. And I'm going to say it follows that distribution where the mean is equal to 750 and sigma, which is our shorthand. It's the way we describe the population parameter for the standard deviation. It's equal to, I don't know, let's say 50. So I'm describing this and saying that student test scores in the treatment group are normally distributed with a mean value of 750 and a standard deviation of 50. They're centered at 750, but they're spread around 750, right? And on average, an individual differs from the mean by 50 points, right? And then let's say S control distributed normal. I'm using these subscripts to indicate treatments and control, right? Normal. And here, I'm not going to usually specify mu equals sigma equals. I'm just going to provide you two numbers. So let's say this one is equal to 748 and 50. So this is this way of writing a normal distribution. We can read it as the test score of the control group is distributed normally, has a normal distribution with mean 748 and standard deviation 50. Now, this is not notation we're going to use a lot right now, but this is notation as we proceed, we will use all the time. Okay, these describe probability distributions. So what we want to do is ask, let's make them a little more different. Let's say 700. Now, what we want to do is think about whether the difference between these two, no, let's keep it where it was, because that's what we got. Okay, so we're going to see the difference between mu1, or we'll say mu2, mu treatment minus mu control. Sorry, my kid is much more Pokemon. Is equal to 2, right? And the standard deviation is equal to 50, right? So here we have this kind of xi minus x bar, right? When you think about this, what's the difference between these two groups? And then convert it onto a standard deviation scale, right? And we get this really, really small difference in terms of relative to the group, how big is this change, right? We're kind of standardizing for the distribution of the group itself. I'm going to stop this now because I think it's getting a little far afield. But the idea here is that if we have things on really different scales, we can use the z-score method to compare them, right? Even if the scales of measurement for the different variables are really different, right? Even if they're an order of magnitude different, right? Even if they're dramatically different, we can convert them onto the scale of their own distribution to ask how different are things from each other, right? And this will help us visualize relationships really clearly. So X bar here is the mean, S of X is the standard deviation, right? We have here, again, we already talked about this with the mean. We typically represent the population parameter with the Greek letter, in this case mu for the mean, and the standard deviation is represented usually by the Greek letter sigma, lowercase sigma, right? But we could also write this as SD or S of X, right? I guess in this case it's not S. Sorry, I'm going to keep my notation consistent. We'll call it S T bar and S D of S of T, right? Because it's of this variable. So the sample mean of the treatment test score and the sample standard deviation of the treatment test score. Right? This notation stuff is going to be uncomfortable at first, but as we keep pushing, it'll, I think, be helpful to start being exposed to this stuff and start thinking in these terms. Okay, so for a normally distributed variable, our z-scores will almost always be between -3 and 3 because of the definition of how a normal works. But in R, we can just use the scale function to do this automatically. So the scale function will do this computation over a vector for us. It will take each observation, subtract out the mean of the vector, divide it by the standard deviation. Okay, so why the hell would we do this? Let's look at our secondary schooling variable. So secondary schooling is on this percentage scale, right? But we don't really know compared to what. Is 3 high, is 3 low, is 74 high, is 74 low? We want to maybe compare those countries that are low on the value to those countries that are high on the value. So if we use the scale function, where I could do a mutate and convert secondary schooling to secondary scale, I'll scale secondary schooling, and you can see that I've converted it now onto a continuous scale that ranges from -1.3 to 3.2, right? So I've taken now this minimum is 3.1 minus 24 divided by the standard deviation of secondary schooling gives me this -1.3 number, right? And the maximum becomes 3.16. So I've rescaled this to this. They're perfectly correlated, right? The correlation between this and this is 1. They measure the same thing. Knowing information about secondary schooling provides me perfect information about the location of this scale variable. But, right, so we have a perfect correlation here. If I plot them out, we've just taken all of these points and remapped them onto a -1 to 3 space instead of a 0 to 100 space. That's what a z-score does, is it remaps things onto a different space. Why would we do that? It turns out it's actually really useful to do when things are on very different units of measurement, right? So correlation, the definition of correlation mathematically is technically the product of the z-scores, the average product of the z-scores of all the two variables together. We're not going to really work through that, but we can use core to do that. And z-scores are going to be something we see often, especially, for example, like if I want to look at the association between, say, income and years of education. In the United States, we measure income on what scale? The minimum is 0, right? The max, I guess you could have negative income. The maximum would be, potentially in the billions or whatever. But it's a massive scale. Years of education, though, the maximum, is theoretically like 5 minus your years of life or something, right? In terms of formal schooling, right? You start in kindergarten at age 5, and then you could keep going to school forever, I guess. But most of us don't do that, who are not, a bit absurd and just want to stay in college forever like me. But most of us don't do that. And we stop school at some point, right? So we can say 16 is a college education. But if income goes up to like 150,000 and college education goes up to 16, right? I could imagine if I want to think about this as what's the slope of the line between income and education, right? For a $1 increase, how much more education do I expect a person to have? Is that slope going to be big or small? Right? The unit of, if I'm asking it in terms of a line, So let's say years of education is equal to, let's call it alpha times income. If I'm measuring income in dollars, do I expect alpha to be big or small? Very small. Why? Because the range of this goes to like 0, let's say 20. But the range of this goes from 0 to, let's say, 1 times 10 to the 6th. Right? They're on really different scales. So even if there's a very strong association between income and education, alpha is going to be small because this scale is so huge relative to this scale. Right? So even if it's a really strong relationship, we may not see it if we're just eyeballing the data, because this is probably going to be like 0.0001 on this scale. $1 in increased income equals, one 10,000th of an increase in year of education in order for the linear function to work appropriately, right? It's going to look like it's nothing. But if we were to Z transform this, a $1 increase in education is that a meaningful difference? No, right? We would want to think about it in terms of what's a meaningful difference in income. And the easiest way to define a meaningful difference is to use the distribution of the data itself. So we can transform this into Z of years and is equal to alpha Z of income, where we put them on the standard deviation scale. So here alpha is going to be equal to like 0.001, but here alpha is probably going to be equal to like 0.4. Once we turn them into standard deviation points, it can really help us visualize relationships between things that are on very different scales. You'll see this come up in practice a lot, but it's a transformation that preserves the linear relationship. It just reshapes it. It just reshapes it. So our school and no media correlated. Actually, I would say it was a minus 0.4. It's actually a minus 0.6. To compute the correlation coefficient here, I use the core function, secondary school, no media, and I need to provide the argument use equals complete to use only those cases where I have observations for both variables. There's some missingness, and that'll screw us up. The z-score method, you can see, will give us the same result, right? There's some rounding error differences, but I can multiply the z-scores by each other and take the average product of the z-scores to get the correlation coefficient, right? Don't worry too much about that. Okay, so where are we at? I'll talk about clustering next time. Sorry, I had a lot more planned today, but we'll do it next time. We get to talk about k-means algorithms. These are really fun. Right? Look at that. This is machine learning right here. It'll be really fun. We're going to kind of use some automated techniques to search out latent structures in our data. But we'll start that next time. I have a homework assigned. We're going to do 2 weeks on this one. Because we didn't finish the material today. So you can start on the homework now, but it won't be due next week. It'll be due the following week. So and this one is a bit harder. It is a real world data analysis challenge, kind of like the one we did with the STAR test. So take your time with it, load in the data, get familiar with it. And people have struggled with this one in the past because the structure of the study is kind of odd. It's a vignette study, which means they kind of tell the respondents a story and then ask them to kind of arrange elements of the story in particular ways. So the study design is a little tricky. So take some time to think about it and understand it. And feel free to ask questions on the Slack. I'll open the channel now. But yeah, that one's open. And yeah, it's again, I like those homework. They are tricky, but I feel like it's actual practice doing the kind of thing that you're going to have to do as, real world data analysts. So, okay. Bye. And office hours now, if you want to talk about anything. No, it's not.